Hi guys! Today we're gonna be talking about my ray tracing application I have written in year around 2014, and now this is open source in my GitHub. The project is Light and Geometry and it is C++ 98 project. Let's delve into this. You can see the rendering is going on in the background here in my application. So what happens here, we have anti-aliasing, we have soft shadows, we have reflections. I'm going to turn everything off now. First of all, I'm going to turn off anti-aliasing off, soft shadows off, and shadows, and no reflections. So this is the effect of ray tracing of the shapes. That's it. No reflections, no shadows, no anti-aliasing. I can turn anti-aliasing on. You can see the second stage is anti-aliasing. It's a little bit slower now, but you can see the soft edges right on the balls and on those shapes here. Now I'll keep the anti-aliasing off for a moment because it's faster this way. I'm going to show you the shadows now. So this is the hard shadows, right? So for every pixel on the screen, I'm finding an intersection of my ray that goes through that pixel on the screen with the geometry. For example, here, this pixel. And it hits this manifold shape, and then what I do, from that pixel I track to the lights. There is two lights. We can see that there is two lights because there is two specular lightnings on those balls, so we know that one light is somewhere there and another light is somewhere there, just based on what is here on those reflections of the lights. So yeah, so we're gonna go from this pixel to that light in there, and we're gonna go from that pixel to that light in there, and we're gonna see if we encounter any objects on our way. The color of the pixel, for example this one here, will be the color of this manifold, okay, multiplied by the illumination at that point. And the illumination at that point is an accumulation of all illuminations from all the lights. So we know that this sphere is occluding the path to this light that's there. So there is zero illumination from that light there, but we still have illumination from the light behind us, right? So we have some shadow from this light here, but we still don't have it completely black because there is still light here, right? This one here, this is a black shadow, so this fragment doesn't get any illumination. It's completely behind the objects. So the light, this one and this one, they don't reach this face, right? They don't reach this face. And this is fully illuminated. So this means there is no objects on the way from those lights, this one and this one. So it's fully illuminated and it has a full color of this cube. Now I can enable soft shadows. What soft shadows do is, for every pixel we send multiple rays into the direction of the lights. So we kind of make lights bigger. So previously in the hard shadows the light was just a point, and with soft shadows we kind of make a light being like a wider array of little points, and we send ray to each of those points, right? So it's like an array, a grid, and we send number of rays, 9 rays to see if any of those rays will hit any object on the way. And we sum this up and we calculate the coverage, right? So on this edge here there is a lesser coverage, so it's softer, and here there is more coverage, so we have full shadow. We still have full shade here because no light can arrive here, and you can see here on this edge how nicely the soft shadow works, right? Looks very specific in this rendering technique. Yeah, so this is the soft shadows. Now the reflections, how the reflections work. So I will enable now the single recursion. So this means we just track one reflection. So for every pixel, for example this pixel here, we have let's turn off the shadows as well. Just keep reflection, nothing else, just reflection. So this pixel here, right, the ray from one of my viewing point hits that pixel And at that pixel, the surface has some, you know, is at some angle between us and some object that is reflecting the surface. So you can see that I think this ball is being reflected here. And what happens is we go from this pixel and reflect our ray against the normal at that pixel, right? And this reflected ray, we test if it hits an object on the way, and it probably hit this ball. I'm gonna show you in Paint here how this looks like. So imagine that this manifold is some this is some surface, right? I'm just gonna go and draw a two-dimensional cross section. So this is the manifold. Now at some point there is this normal vector, okay? And this is the point where our ray from here, from our eye. So this is our eye here, okay? And we're going, and this is our ray, right? So the ray is just a unit vector maybe, or it doesn't need to be unit vector actually in this software. I normalize when it's needed, only when it's needed, because normalization costs computation, so I avoid normalization whenever I can. So I have a ray that goes into that point on my manifold, and at that point there is some normal vector. So this normal vector, let's call it n, and let's call this ray direction is v, okay? We don't care about the origin of the ray, it could be u, but this point is unnecessary to know at this stage. We're just calculating the reflection of the vector. So we need to move this in here, so make the origin of this v here. So we just copy this vector, okay? So that's our ray vector. And we're gonna do this trick. We're gonna take this normal and we're gonna go this way, okay? So we're gonna extend the normal in depth. Now the normal vector has this length, okay? So that's a unit vector of normal vector. So that's where it's 1 unit of the normal vector. And then we project this v vector, this one here. This is also v vector. So this v vector and this is the same v vector. It's just attached in this different origin. And we project it here onto this normal vector, right? When we project it, we have this projection here. Okay, so that is the shadow of this v vector onto this normal. And if we multiply this by the normal vector, we will have this vector like this. Okay, so this is the right. This here is important. This is the right angle here. So it's right angle. Now, if I subtract this vector from the v, then the resulting vector will be like this. Okay, it will be like this. So you know, I'm subtracting this vector, right? So this is what will happen. That's not a reflected vector, right? That's more like a tangent vector, but it's not a reflected vector. So let's subtract 2 of those orange vectors. We subtract 2 of them, okay? And look what happens. We end up with a reflected vector v, right? So this is the v reflected, and this is how our vector v got reflected from this at this point, you know, around this normal. So the properties here are that this angle here and this angle here are the same, and let's use the different color, maybe the brown, and these 2 angles, this one and this one, are the same angles, right? So this is how we know they're reflected. Then this reflected vector is a ray that goes somewhere, right? I'm just going drawing here an arrow, but the vector is just here. And it may hit some object on the way. Oh, here's the object. And this object is gonna be reflecting in this point here, right? So what we're doing, we have a color of this object, the original object, so we're hitting this manifold, which is yellow. So we have this color of this object, and we're reflecting our vector, okay, and it hits another object and it has a different color, right? So let's say this object was yellow, okay, this object was yellow. Let's put it yellow here just to show it. And this object is kind of all brownish, right? It's kind of brownish, so we can use brown here. It's not a big difference of colors, But for example, those objects here, they have a different color. So this one is blue, this one is yellow. More interesting, you end up with having green color when you mix them together. And I tell you how this happens actually. So because this one is yellow and this one is brownish, let's actually make it blue. Why not to make it blue like this one here? So if this one is blue and this one is yellow, the surface that we're reflecting from might have a property that it is filtering color. It's metallic, for example. If it's a metallic surface, it will not be reflecting light as is. It might colorize the reflection with this yellow color, right? So it's metallic objects that color, like gold, for example. In gold, you would have everything reflected, colored in gold, right? If it is a plastic, then in plastic things tend to reflect without changing color, right? So so this yellow will affect this blue, and the reflected image of this will be here, will be green, right? So for each point here that we're rendering, because this is just one point, we're going to be rendering a number of points, and they will be reflecting into this shape here, right? And the image will be mix of this blue and this yellow, and as a result we'll have the green image, right? So that's how the reflections work here. Let's see what happens when we have multiple recursions. So this is 2 recursions now. So what happened here, we have a reflection here of this ball, but then in this ball there is a reflection of something of this manifold, I suppose, right? And if I go more recursions, we will have more reflections tracked, So 1 recursion, that's no recursion, it's just 1 reflection. 2 recursions, we reflect in the reflected object. 3 recursions, the reflection of reflection, right? So let me just show you on the picture here. I have this one object, the ray is reflected, right? There's another object, the ray is reflected, okay? And then the ray maybe is reflected, and then maybe the ray is reflected, So depending on number of recursions, we can keep going. We can keep going to infinity with this until we either find no reflection or we keep just bouncing, right? So those are recursions. Now, what is shadows? Let me show you how shadows work. So shadows look like this. So we have a surface here, this manifold. This is our eye, okay, looking at it. There is this ray here going into this manifold, okay? And we try to say what is the color in this place. And it will be this yellow, okay? It will be this yellow, but because the surface is yellow. But for that to happen, there has to be some light that illuminates it. If there is no light, there is no color, right? The only reason we see any colors is because there is light. So let's say there is a light here, okay? And this light illuminates this pixel, okay? It just illuminates this pixel. But let's say there is an object here, okay? Let's say there is an object here, and you see for this pixel here, this light will encounter this object, and there won't be light in this pixel, right? This pixel will be in the shadow of this object. So what we do when we try to render that other pixel, okay? We track to the light. We can track this way or this way. It really doesn't matter, because what we care about is there anything on the way? Because if there is anything on the way, then there is no light. If there's nothing on the way, then we have light here, right? So that's how shadows work. Soft shadows work in a way that I can move this light a bit, okay? To the left, to the right, whichever. I'm actually creating this sort of grid. So if this is in 3D, then this is like a grid. So this is my original position of light, and I move it into those 8 other locations. So see the 2 other locations, and then in this direction as well. and I see, okay, will this pixel be illuminated if I go from here? Also not, right? This pixel won't be illuminated. But if I go at the edge here, right? So if I go here, so you can see that maybe this pixel will have some partial illumination, right? This pixel is in a shadow from this place. Maybe it's in the shadow from this place as well, right? But it's not in the shadow in this place. So if it's in this view here, we have just 3 positions of light, but this will be 9 positions of light, right? But out of these 9, let's say these 3 positions would get, you know, true to this point, right? So you'd have 1/3 of all illumination, right? So this pixel will be illuminated in 1/3. So let me just show you the soft shadows. So we have here the soft shadows. So these pixels are partially illuminated, right, from this light above. That's how this works. Now, how does the anti-aliasing work? So let me turn the anti-aliasing on. So you can see the second pass, you can see this brighter. So I deliberately render it this way. It's for presentation purposes only, because the first pass that rendered this is unnecessary. It's just to show you the scene before I render the full pass with all anti-aliasing and everything. So this is only like so that it's easier to see what's going on. Let me just demonstrate you what is anti-aliasing doing. So we have some objects on the scene, okay, and we have this eye here, and from the eye we have this number of rays, right? So they have this ray that goes in here, and there is nothing in there. We have this ray that goes here, and there is this object. We have this ray that goes here, and there is this object. But, you know, in this space here, in this space in between objects, you know, you would have like a very jaggy edges, right? You would have either ray goes through or it doesn't go through, and then you would have objects that should be nice and round and smooth, like here this result. If I turn off anti-aliasing, you can see this edges here. This is so kind of jaggy because this is polygonal model and this is the analytical model. So you can see that this one is nice and soft. If I turn off the anti-aliasing, you should see like it's jagged, right? This thing here is jagged. It's not so, here you see it's jagged. It's not so soft. It's not so nice, right? And the reason it's jagged and not so soft is because the ray from the eye to that point either hits this ball or it doesn't hit the ball. So it either has a color of whatever the color must be, or it doesn't have any color, right? And with anti-aliasing, we kind of accumulate, you know, number of rays that go there. So if I were to draw this situation, so maybe let me draw it again with a new picture. This is our eye. Now we have this sphere here. We have this ray that goes and maybe hits the sphere, okay? Maybe this one doesn't, and maybe this one does, and maybe this one doesn't, right? So what we're doing, I'm creating this again, this kind of grid, 4x4, where I'm you know, shooting 16 different rays from this eye, right? So for each of those places, you know, I'm for just to render one pixel, I'm shooting 16 rays and testing. Is there an intersection? Is there an intersection? Is there intersection? No intersection. So there is a coverage of, in this case, 1/3. So intersection, yes. 0, no intersection, no intersection, right? So this way we have these nice and soft edges, right? So that's our anti-aliasing. So how do we actually render this image? So this is our Frustum, okay? And just use brighter color here. Just show you like this. Okay, so this is our Frustum. Now this is our eye, and this is the left, this is right. Okay, this is also top, and this is bottom. Okay, so what we're doing, we're just dividing this surface, okay, this rectangle here on this plane, into as many bits, as many pixels you want to render, okay? So if you want to render HD image, then it will be 1920 by 1080. So you just divide the space right minus left by 1920 and bottom minus top by 1080, okay? And then you'll have this delta. You'll have this delta here, and you'll have this delta here, okay? And you just apply this delta again to move your ray. Now, I'm not rotating the ray, I'm just applying the delta. So I'm creating rays like this, from here to here. That's my ray number 1, okay? Then ray number 2 will be, I add this delta, and it's gonna go from here to here, okay? And then I apply delta, and I'm gonna go here. And I apply delta, and I go here. And I apply delta, and I go here. So each of those rays have different length. And the algorithm I'm using, they don't really care if the ray is unit vector length, okay? It can be whatever length. So for every pixel, I have a different length of the ray. But this is how I generate them, right? So I have these deltas. I have this X delta and Y delta. So if I want to render second row, I'm going to obviously apply Y delta, and that's my second row, first ray, second ray, and so on. So this is what I'm doing. So I'm going like, right? So yeah, so this is the method of generating rays when I have this kind of like grid. Again, they're not non-unit vectors. We can turn them into unit vectors by dividing by length if we want to. And yeah, and we just test those rays against the scene. If they hit something, we render the color. All right, let's see the architecture of this ray tracing program. So it's designed in a quite classical way. So we have this app class, which is an abstract class, basically receiving events, and we implement a Raytracer, okay? So the Raytracer has these properties here. So the camera, the scene, and the target buffer, okay? And if we look at the scene graph, you'll see there's lights, and there's a list of objects, which is a list of clumps, okay? Those things here. And clump itself is just a bunch of geometries, okay? So it has a list as well, which is a list of geometries, okay? So the way this is structured is Raytracer has a scene, the scene has lights and the clumps have geometries, and geometries can be one of those. So then can be sphere, cylinder, or mesh. You can see it here. We have an abstract class geometry with virtual method doIntersectRay, and then we have a sphere, cylinder, and mesh geometry. Okay, so this is the architecture. Now the ray tracing starts with Raytracer thread. So there is as many threads, as many CPU cores we have, and I can actually show you that. So I'm gonna launch Task Manager. This is my 12-core Ryzen 9 with 24 threads, and if I force re-render, you can see that all 24 threads are doing work right now, rendering, and you can see that each thread is rendering just one line of the image, right? So this is how it was using the CPU. It was using it in parallel, all the 24 cores at once. All right, so what does one ray tracing thread do? One ray tracing thread will render every end line of the image. So we just say, which thread am I? How many threads there are? So how many threads will tell me what's the offset between lines to render. So if there's 24 threads, I'm going to be picking every 24th line, and thread number is, am I thread 0, then I'm starting with first line. Am I thread 1, then I'm starting for second line, and so on, right? So calculate lines will produce a vector of those traceline infos, which just say which lines should be rendered. So this is quite static. So if I wanted to make those objects somehow move, animate, I don't have to recalculate those lines for every time I want to re-render. This is a static Raytracer at this moment, so this is just calculating those lines. But another advantage that I have from calculating those lines prior tracing them is that I can actually reorder them. So if you look again, right now I kind of rendered that in a different order. I didn't go from the beginning to the end. I just picked some lines, then some lines, then some lines. Just look again. You see? So this is to improve presentation, right? When I'm manipulating with the image, for example. So we have two passes. We have this first pass, which is disabling the anti-aliasing, okay? And it's rendered in slightly darker colors, so I use 80% of the brightness here. And the final pass, which is using full brightness. So this way we can see how this second pass is actually progressing because it's using full brightness, right? Okay, so what does the ray trace lines do? The ray trace lines in the camera will take the trace lines we have calculated, and for every line and every pixel, okay, it will call ray trace, or we'll call do FSAA. So if we're doing anti-aliasing, as I mentioned earlier, we're creating this mesh 4x4 of rays. Okay, so we have these 4 rays that will be casted to get the color of 1 pixel. So this is what we're doing in this double loop here, and we call a ray trace. Okay, and what is ray trace doing? Ray trace is essentially calling a ray trace on the scene graph. Okay, so if we go back to our design, so we started with Raytracer. It says to camera to ray trace, okay, and we pass, as you see, scene graph is past the parameter. So we say, hey camera, this is your scene, render it, and this is the scene. So we have Raytracer, we have a camera, and we have a scene graph. So we say, camera, render me the scene, okay, and yeah, and then we say scene graph ray trace with the ray. So we have some ray here that we want to cast, and we want to test if this ray will hit something, what will be the color, okay? So the scene graph ray trace ray with recursion depth, we also set the recursion. This will actually render, this will actually render the pixel, okay? Now, the result of this rendering is just a color, because we're rendering 1 pixel, okay? So if ray trace means I have a ray from my eye going somewhere, and I just want to know what will be the color in that pixel. That's all it does. It returns a color. That's all it returns. So this ray trace, if we can look again, will go into scene graph, and scene graph will use the lights to illuminate the pixel. Okay, so it will first find some geometry that we are hitting. So it will scan all the clumps. It will find which geometry was hit in which position, in which point in the space, and then it will use the lights to illuminate it. So let's see that in the code. So first thing we do, we call intersect ray. Okay, so we have this ray, intersecting it, and the intersect ray calls do intersect ray, which is going over all geometries in the list, and it calls intersect ray on geometries. Okay, so we scan all geometries, we see, oh, is there an intersection with this geometry? Okay, and then after we intersected it, we call shade, and shade goes over the lights. So it goes over the lights and tells the lights to illuminate that pixel, that point in space. So we have this intersection point. So look at that. Intersect ray will take the ray and intersect it with the geometries, and the result will be an intersection point on some geometry. We don't really care what geometry the point is on. For us, it's just a point in space. It has a color, okay? We know whether it is reflective or not, maybe. Alright, let's go down and see what light illuminate does. So light illuminate in the light class, okay, so we're now here in this light class, we have the scene graph, we have a ray, and we have an intersection point, right? So we are somewhere, we have a ray that goes there, and now we need to find the light that would illuminate this point. So what we're gonna do is we see if we want to drop a shadow on that point, right? So that's one thing, if shadows are enabled. So first of all, if I disable shadows, right now shadows are not enabled, so what we're gonna do, we're just gonna process the light. To process the light, you can still see that there is some shading going on. There is some specular, there is some shading going on. So for this shading to happen, we take the angle between the normal vector at this incidence points where we intersected our ray with this intersection, right? And we check what's the angle between light and the normal vector, how much light will be reflected in our direction from this point, right? And specular reflections are places where most of, like, where we're looking and the light will be literally in our eyes, you know. So then the reflection of our ray will go almost straight into the light, and that's our specular. Then I'm doing this intensity of the light will be 1 minus the soft shadow, right? So in a case of hard shadows, we just say if there's a shadow, it's just black. Okay, so no shadow, hard shadow, so it's just black. Okay, it's just no black or black. But it's not black because, as we see in the scene graph, we iterate over a number of lights and we illuminate from every light. So if one light returned no illumination, zero illumination, there is still another light that can return some illumination. So we sum those illuminations. It's a sum. It's not average, it's a sum, because every light adds to illumination. Every light makes it more illuminated, right? So this is what lights do. Okay, so what happens with the soft shadow? So soft shadows, as you can see here on the picture, create soft edges, and for that I'm creating a loop here, double loop. It's a, it's a grid 3 by 3. So I just pretend that light is not a point light. It's more like an area light where it's bigger. It's not just one point, right? So if I were to draw it, it would be similar to this, right? So we have this geometry here. We have this point here, okay? And then from this point, we go to this grid created for the light. So that's our grid, And what we're doing, we're intersecting all those rays that will be, in this frustum. Okay, we're creating this frustum like this. So this is all one kind of like area light now, okay? So from every point of this grid, we send a light into this point. Instead of just one point, we create kind of like 9 point lights here, and just illuminate this single point from this 9 point lights, The orientation of this surface, of this area, is perpendicular to this main direction of the light into this point, right? So we get the vector from this point to the light, and then this is just a small surface that's perpendicular or orthogonal to this direction. Okay, and we just shift our light in this space. Okay, so what does drop shadow do? So drop shadow, as you can imagine, it calls intersect ray again, but this time we're intersecting light ray. So initially we're intersecting a ray from, from our eye. We're looking into this ray that goes from our eye into this point, right? This ray, and we hit some geometry here. But now we're intersecting light rays. So light ray is this one here, right? And we're intersecting those light rays, all of them, like this one, all of those light rays, right? And then we know what's the illumination of this point from this light. Okay, so in this drop shadow, we just calculate intersection with one of those light rays. And in soft shadow, we generated all those rays for this real light. So we repeatedly call this drop shadow. So we repeatedly call intersect ray for each of those little light rays. And once we intersect, we have the intersection point. Based on that, we know whether there was something in the way or not, whether there was some object here in the way, dropping some shadow or not, right? So this is our illumination with soft shadows as well. Okay, so at this stage, I think we understand the anatomy of this ray tracing program. How about we see how does the intersection with those objects work, right? So we have these three different geometries possible: sphere, cylinder, and mesh. Mesh is just a traditional, structure made of triangles. Sphere and cylinder are analytical shapes, okay? So they are continuous, they don't contain any triangles, okay? So let's see how those intersections are made. So sphere geometry will use intersect ray sphere. That's a special function I have in my library, I have written some time ago. And then cylinder has this little bit logic here, but it also calls intersect ray infinite cylinder. So intersect ray infinite cylinder is essentially the same thing as intersect ray sphere. It just reduces the dimensionality from 3D into 2D. It flattens, right? Because when you flatten the sphere, you get a circle. When you flatten an infinite cylinder, you also get a circle. So you have the same problem to solve, right? And then you need to check if we are, below cylinder, above cylinder. So these are the additional checks we have here. And eventually we just calculate the position where we would be intersecting. For mesh geometry, we have two intersections tested. We have test with bounding sphere, okay? So there is a bounding sphere defining whether the mesh, where the mesh exists. That speeds up the whole tracing. And then if ray does intersect this sphere, the bounding sphere, then we go down the rabbit hole and we intersect with all triangles in the mesh. We have intersect ray triangle, okay? So this is our function we call in our library. Now, you may wonder how these objects are placed in different locations, right? So every geometry is placed in the scene using the translation and the local transfer matrix. The local transfer matrix has to remain orthogonal, so it can represent the rotation. The translation is not part of the matrix, right? And the reason for that is because I'm using the transpose to create an inverse. And for rotations, transpose is an inverse, so it works perfectly, right? So first thing we do in the base class geometry is we do transform. So we do inverse transform of local transformation matrix. So we do inverse transform of the ray direction, and we apply inverse translation, okay? So this way we transform ray from global world coordinates into local geometric coordinates. So after this operation, ray is expressed in local coordinates of the geometry, meaning that the center of the geometry is 0 of this space. And then we call the virtual abstract do intersect ray. which is performing the actual intersection. Here I have this little library I have written for intersections. So we have the ray defined here, okay, as a start and direction, and we have a solution defined as some number of numeric values, okay. We have number of intersection functions like intersect ray plane, intersect ray sphere, intersect ray infinite cylinder, and intersect ray triangle by edges. This is by edges, but then you also have by points, which calls by edges, so it does the computation here. So this way we can perform intersection of all the shapes in the scene using those functions. The ray triangle intersection algorithm is from this white paper here. I based it on this white paper. This is Müller-Trumbull algorithm, and it's using this approach. I'm going to show you the white paper. So this is the white paper, which talks about ray triangle intersection in a fast, efficient way. What we're doing here, we're moving triangle into new coordinate space so that its first vertex is at 0, okay? And then we transform this space, so this is still, word aligned axis. We transform it so that we have a space where edges of the triangle are 2 axes of the space, and the direction of the ray is a 3rd axis of the space. So on this axis you have a ray is parallel to this axis, and then those 2 axes are on the edges of the triangle. And then finding out if the ray is intersecting triangle is as simple as telling how far the ray is from the point 0, right? So this is what we're doing here in this code. The paper shows that we need to calculate this determinants, okay? And it explains that those determinants can be calculated by doing cross product and the dot product. It also finds that certain cross products are repeated, so you can see T cross E1 is repeated twice, D cross E2 is also repeated twice, so we just need 2 cross products, Q and P, as shown here. So we end up with just 2 cross products, so we have a cross product here, and we have a cross product here, okay? And we have 4 dot products, so this is a 3 and 1, right? So we have 1 dot product, 2, 3 and 4. So that's very cheap compared to other method of calculating a ray triangle intersection. So what about a ray sphere intersection? Well, what I'm doing is, this is our sphere, okay, and this is our ray. It's obvious from this picture that the ray will intersect in 2 places, this sphere. There might be another ray that actually is tangent with the sphere here, and there is another ray that might not be intersecting the sphere, right? So this one might have one solution. We may consider it as no solution, because if it's tangent, then does it intersect? Does it not intersect? Let's say it intersects. Where does the light go? What do we render? You see, the ray will go straight forward, right? It will not reflect anywhere. So we probably want to just say in both cases there's no intersection. We're only interested in this intersection point here. And the reason is that because in this intersection here, this ray has a chance to reflect into either, some object and have a reflection there, or there might be some light and we can illuminate it. We have this ray starting here, going here, and if this is U and this is V, right? So we have U start relative to sphere center, and we said that everything is relative to our geometry center because we apply this local transform matrix. And we have V, which is ray direction, so this is ray direction. Actually the direction will be here attached to the center because it's a vector. Vectors don't have position in the space. And we have this U relative to this origin, so U is more like this vector here, okay? So that's our U. What we do in this solution here for ray sphere intersection, we represent any point on sphere as p, and we say that p squared is equal r squared. Okay, this is our representation of the point on a sphere. Now, because this p is x, y, z, okay, so p squared will be x squared plus y squared plus z squared, right? Because this is a dot product of p with itself. Okay, so if you are not familiar with square of the vector, it's just a dot product. Okay, so p is a point on a sphere. Okay, now we want that point on the sphere to be the same point as point on the ray. How do we define ray if we know the start and the direction? We can define ray as, you know, this u, the starting point, plus some parameter k times this direction v, right? So that's our ray. So we just put this as our point on the sphere. Okay, if I put this as our point on the sphere into this equation, then we have a quadratic equation, right? Why are we doing this? Because we just said this p is a point on the sphere, and this is a function defining the ray. So a point on the ray has to be the same as point on the sphere. So we just take this as p, right? As this point on the sphere. And when we put it there and we square it, we're gonna have a quadratic equation, okay? And that's why we're solving the quadratic here. So we're doing those dot products because obviously that's what happens when we try to solve this, okay? So you need to square it. You will see that you will have u square plus u k v plus v squared, right? That's plus. So that's also a vector, right? So you will have a dot product of u with u. So that's dot product start and start. You have a dot product of VV, so the direction, and you have a dot product U and V, which is start and direction, okay? And we do minus sphere radius. So what we actually do, we change this equation to be p squared minus radius squared equals 0. So that's the equation we want to solve, right? So minus r squared, so that's what we do here, minus radius squared. So that's our ABC. It's C, right? Because U and R squared, those two are constant. We don't change it. The solution is K, right? It is the K that's the solution. Yeah, so here we have K squared. Okay, that's our intersect ray sphere algorithm. The intersect ray infinite cylinder simply does transformation and turns everything into ray sphere problem. Okay, we just flatten the whole problem, right? So the sphere will be having 3D. We just flatten into just a circle, and the ray, wherever it is, we just flatten it, just project everything on one plane, and we have this, you know, planar ray. Okay. So we actually, you know, we actually intersect two-dimensional ray with two-dimensional sphere. Yeah, so that's the intersections. So how do we do all this, you know, vector by matrix and matrix by matrix multiplications, or dot products and cross products? Here's the library I have created in C++ 98. It's implemented in fully functional programming fashion. So because it's C++ 98, I had to define those operators. I couldn't use lambda, right? So these are the operators for addition, multiplication, and so on. And this is the fold operation, okay? So this is recursive fold. It allows you to fold in a pairwise manner or over elements with a constant, or to aggregate, right, to accumulate, or without any arguments, right? So so that's our fold, and it's recursive implementation. So this is fold defined for I, size I, dimensionality I, and this is fold defined for dimensionality of 1. So for dimensionality of I, it's apply fold for I minus 1 dimensionality plus do the operation. You can see here. So and it goes recursively until I minus 1 is 1, and then this implementation is used. So this is specialization for 1. Class point is essentially an array of dimensionality I. Okay, so you specify the type, like for example double and 3. So you have point 3D would be point of 3 doubles. And you can see that, for example, operator addition is defined as a fold over this array and the other vector. So it's a template type so that you can actually add to a point of 3 doubles, a point of 3 floats, or a point of 3 integers even, right? So this is how flexible this is. Multiplication is using the unary fold operator, so it folds over elements of this array with this operation, and this is a constant that's used over every element. There's also, for example, negation. So this is the fold that is accumulating over all the elements of this array with this accumulator. This is the accumulator. So it starts with false, and then we accumulate until maybe it will become true, right? So then we define points of different dimensionalities, point of dimension 1, 2, 3, and 4. And for each of these dimensionalities, then we define for given types. So we have points for bytes, integers, floats, and doubles of dimension 1, of dimension 2, 3, and 4. So this is point, and then we define a matrix. And matrix will use some cool things like transposition, transpose, and a few other operators here for our operations. So if we had a fold operator that was taking operators, so we can use that operator with this new operator which is using fold internally. So this is going to be a fold over the fold, so this will be used in matrices. If you look here, we have, for example, addition. So what does it mean to add a matrix to a matrix? It means to add every vector in one matrix with its corresponding vector in the other matrix and construct a matrix. So this is why I do this, fold over this guy, which is going to be doing also a fold of addition, right? So two-dimensional fold. Multiplication with scalar will be the same. We just apply unary, so they just go over all elements of our matrix and try to multiply them by the constant scalar. So we multiply every vector in our matrix by this scalar, and then every vector needs to be multiplied by scalar also using fold. So it's a fold over fold again. And then we define matrices of different sizes, 1, 2, 3, and 4, and different data types, integer, float, double. And you may ask, so how do we multiply matrix by vector? So we have operator that does it, multiply matrix by vector, and it's using this, and then again another functional construct here. So multiply row, so we take matrix and vector. It uses a thing called transposition here to multiply vector by columns of the matrix, okay? So each element of this vector V needs to be multiplied by each column of this matrix M, so that's why we need to do transposition. When we multiply matrix by matrix, we do the same thing we fold over all vectors in one matrix. So we multiply vectors in one matrix by rows in the other matrix, okay? And that's our functional way of doing it. And then we define things like cross product. So cross product for dimensionality of 2 is, hard coded. It's just this calculation. That's it. Okay. for dimensionality of 3 is defined like this. I don't have a generic version of cross product, it's only for dimension 2 and 3. Dot product is defined in generic way, so it's a fold where we do multiplication and then addition. Okay, so I actually define the sum as well. Square length is we square each element of the vector and then we sum the result into one scalar. Length is the square root of that. Distance is a square sum of a difference between two vectors, okay, or 2 points. And cosinus is a dot product of the two vectors divided by square root of, you know, two square lengths multiplied together of two vectors. Right, so that's how we calculate all these things. And then I have these utility functions that calculate reflection. So the reflect, okay, and the project to plane function, which will project, you know, a point to a plane expressed by normal. And then we have a project. We can project a point into a vector. So again, it's a dot product, normal by r times k. So it's not just dot product, but it gives you a vector. And then you have orthogonal vectors. So for any vector, you can produce some orthogonal vector, okay? And it will be some random orthogonal vector. It might be, you know, an orthogonal vector that's calculated as a, you know, cross product between the vector and the up vector, or the vector and a left vector, you know. So this is the two outcomes here. So this avoids calculating costly cross product because up vector has coordinates 0, 1, 0 and left vector has coordinates 1, 0, 0. So this is known outcome. And then we have Euler rotation about each axis, so we can just rotate objects using this and it will generate a matrix for you. So that's my you know, linear algebra and geometry library. Alright, so this is my ray tracing program. It's on my GitHub and you are welcome to try it out. The purpose of this program is more educational. It's to just have a reference for how to do those things, okay? This application isn't designed to be fast. It's not designed for performance, although as we have seen, it's using the fast triangle intersection algorithm, as well as it's using bounding sphere for the mesh geometries. The improvement here could be the scene could be divided into sectors, so we could create a binary spanning tree, okay? So it's a binary tree where we use planes to divide the space, and then the ray intersection could be just limited to objects in those sectors where the ray is intersecting. So in this area, these objects wouldn't be there. That would speed up rendering as well. So that's something that could be considered. The textures could be added, but that wasn't the goal here. So when we do ray tracing, maybe textures aren't so important in the subject of ray tracing. Texture mapping is a different subject, and perhaps, you know, some other material could be created for that. Thank you for watching. It was a pleasure demonstrating this to you, and please leave any comments and like, subscribe, and see you in next videos.